Welcome to the second video in our discussion on oxidation of carbon. In this video, we'll be focusing specifically on oxidizing a particular functional group, alcohols, and we'll focus on what happens both to the oxygen of an alcohol group, but especially the carbon that's also part of that group. To get started, we'll look at a very generic kind of an example. So we have an alcohol here, and then we could think about changing the oxidation state of the carbon of the alcohol up one level. So from +1 to +2. I'll follow that carbon into the products. Here's C +1, here's C +2. So by introducing this second carbon-oxygen bond that we see in the product, we're effectively oxidizing the carbon that was a part of the alcohol group. Now, the way that this works is actually fairly straightforward from a bond change perspective. So what kinds of structural changes are happening? So I'm going to actually call out these hydrogens that are attached to the carbon being oxidized in blue, and then we can follow what happens when we go to the products. In order to make this carbon-oxygen double bond, I needed to remove the hydrogen from the oxygen, and it turns out I'm also going to need to remove one of these hydrogens from the carbon in order to stay at the octet and not go over. So if I actually look at what's happening here, I see the R group and the carbon and the oxygen and one of the blue hydrogens in my product, but it seems like I'm missing the other blue hydrogen and the hydrogen from our OH group, which means that formally, when I oxidize an alcohol, I'm making H2 also. So this would be like a generic oxidation. There's no reagents involved yet. We'll talk about some specific kinds of reagents we use to do these reactions. If all we mean is some kind of oxidation, we'll write O in brackets to denote that we're doing an oxidation. And typically what we think about is that every oxidation that we do of a carbon, so for instance going from C +1 to C +2, we're going to effectively be removing an equivalent of H2 from that molecule. So there are literally thousands of oxidation reactions of alcohols. I kid you not, I have a book. It's about 1,500 pages long, and hundreds of those pages are just this kind of a reaction. But at their heart, they all do the exact same thing, this type of generic transformation. And the choice of reagents you would use to affect this are going to be practical considerations about maybe what's in your lab, what other kinds of functional groups are in your molecule. So for instance, like what R is, and this extent to which you want to oxidize a carbon. But what all of these reagents have in common is that they have to have an atom that gets reduced. We know that oxidation of carbon or any other element or atom for that matter requires something else to be reduced. We learned about this back in general chemistry. You might have learned some mnemonics like Leo says Gur or oil rig. Those kinds of mnemonics remind you that there's a coupling between an oxidation and a reduction. They have to be happening simultaneously, in essence because we're redirecting electrons from one substrate to another. So in essence, designing an oxidation of an alcohol requires us to choose which atom in particular within a reagent that's going to be easy to reduce. This is essentially like a design principle for coming up with ways to oxidize alcohols. So there's a lot of options. You could choose things like highly electronegative elements, chlorine, oxygen, those kinds of things, and then make them electron poor. Like maybe you could come up somehow with something like Cl+ or O+. We know that those atoms really like electrons, and because they're positively charged, they should be very adept at gaining electrons, which is another way of saying being reduced. Another strategy is actually to use compounds, or specifically atoms, that are at very high oxidation states, maybe like +3, +4, +7, those kinds of things. But we know that really the only way we're going to come up with those kinds of oxidation states is to use transition metals. So one option is to use high oxidation state transition metals. in our oxidizing reagents. And the idea here is that an element like a metal, even though it's not that electronegative, if you make it sufficiently positively charged, it should be relatively facile to put electrons back into it. And in fact, you've already learned about this. So if you think back to your discussion of alkenes in OChem 1, we learned about a reagent called OSO4, or osmium tetroxide. OS, or osmium, is a transition metal, and in this compound, it's osmium at the +8 oxidation state. The idea here is that you're using that very, very low electron density on osmium to drive the oxidation reaction of an alkene into two different alcohol groups. So we'll do something similar with our oxidations of alcohols, but we won't use this reagent. So this is not for alcohol oxidation. But we'll use a similar strategy. Like maybe we could come up with a compound that has a transition metal at a very high oxidation state, and we can use that to drive oxidations of carbons in alcohol groups. One way of doing this is sometimes called the Jones oxidation, named after the chemist that developed this chemistry, or we could take things like secondary alcohols, for instance. So we'll look at like a specific Jones oxidation reaction here. And we mix this with some chromium, CrO3. So this is chromium trioxide. And we know from our oxidation state rules that this is chromium at the +6 oxidation level. So this is our strategy of using a very highly positively charged transition metal as our oxidizing agent. So the other reagents that are involved here are water. This kinds of compounds like chromium trioxide are only very sparingly soluble in any organic solvent. In fact, they're not really soluble in any organic solvent, and only really kind of soluble in water. So to add to the solubility and to activate this reagent, we also add sulfuric acid. So there's a mixture of 3 different compounds here that are all required for the Jones oxidation to work properly. Chromium trioxide, that's the actual oxidant. The chromium atom in particular is the thing that's going to be reduced. Water and sulfuric acid, we could think about those like solvents, although they do play important roles in the reaction as well. And so what we can see is that at the end of the day, we go from a carbon at the +1 level, so I'll star that in the reactants, to a carbon at the +2 level. If we wanted to talk about this in the context of functional groups, we'd say that we had a secondary alcohol, and we ended up with a ketone. So we notice that the only part of the molecule that changes is the carbon and the oxygen, and specifically that we are removing the H from the OH and what I'm calling the blue hydrogen. That's the hydrogen attached to the carbon of the alcohol group. So the aromatic ring, and in this case the methyl, stay the same. Really, this is a very limited change in the structure. So you could write all these reagents down. That's a lot. It's also okay to just call this Jones, and that will denote that these 3 reagents are present. So the Jones oxidation works for a variety of different kinds of alcohols, but for now we'll just focus on doing another example involving a secondary alcohol. So we could look at a similar kind of a compound, but let's make it a little bit more complex now. So we'll put an alkene in. We have something that looks like this, for instance. So what we can do here is react this compound with Jones. Remember, that's going to denote all 3 of these reagents together. And all that's going to change is the alcohol functional group. So for me, I'm always going to make sure that I know where my blue hydrogens are. It's going to be important to be able to find those, and as we'll see later, count them. And I know that that's going to be removed. So what's left for me to do here is simply to redraw the hydrocarbon skeleton, and I'm only going to make changes to the CO bond and remove the relevant hydrogens. So there's my hydrocarbon skeleton. This carbon is here, and I have a ketone there, so that looks like my reaction. All right, the other thing that you could be considering in both of these cases is what happens to the chromium, right? We've been talking a lot about how important this high valent is sometimes called, or highly positively charged chromium atom is, and it turns out that we can find it in the products as a structure that looks something like this. I'm going to put it in quotation marks because this compound is actually kind of polymeric. It's not just a single molecule like this. Think about lots of these that are all stitched together. But if we look at this very carefully, this is now chromium at the +4 oxidation level. So we can see that our chromium is being reduced. and specifically reduced by 2 electrons. So going from +6 to +4, 2 electrons. What we can say then from this observation, and if we study other types of oxidation reactions, you'd see the same thing, as going from, or I should say, 1 carbon oxidation level is going to be equal to 2 electrons. So every carbon level that I change, so like +1 to +2, I'm going to change my reducing agent or my oxidizing agent by 2 electrons, right? So in the alcohol reaction, we'd go from +6 to +4, and that's going to correspond to 1 carbon oxidation level change. So in the next section of this video, we'll be looking at a different type of reaction that the Jones reagents do. It's a little bit of an accident, but I think it's kind of a useful one. In this section, we'll look at what happens when we take primary alcohols and react them in the Jones oxidation reaction. So here we've got 2 of these blue hydrogens, or in essence, this carbon has 2 CH bonds. And so what we might expect initially is the type of pattern we saw before, where we would remove one of these blue hydrogens, remove the H from the oxygen, and put a double bond in there. So we should see something like this. So here we would go from a primary alcohol to an aldehyde. The idea here basically is that I have this residual H, which I should have done in blue. There we go. And that's what makes it an aldehyde instead of a ketone. So the pattern stays the same, introducing a double bond between the C and the O of the alcohol, right? Here's the issue. If you actually do this reaction, there's a variety of ways you could tell whether you actually made an aldehyde. You could use IR to look at things like the carbonyl stretching frequency, or whether you see this CH signal at around 2700 inverse centimeters. You could also use carbon NMR to see whether the chemical shift for a carbon here is around 180 to 190. Or you could look at proton NMR, and you should see something between 9 and 10 ppm for this residual proton that's part of the aldehyde group. We didn't observe any of those things. Which is kind of surprising. Instead, we see something different. We actually see the formation of a carboxylic acid. So we still have all of our methyls and things like that, but the compound that we actually obtain is this. This is the isolated product. And just so for completion's sake, we'll label the functional group carboxylic acid. Interesting. So what happened here? It's not super obvious initially why this would occur. We know that it reliably does occur, that primary alcohols, when treated with the Jones reagents, make carboxylic acids. And it turns out that what happens is the aldehyde does form, but because of the presence of the solvents that we're using, that aldehyde reacts with water to make what's called a hydrate. So just to be a little bit clear, this oxygen is coming from the water molecule. If we look at the hydrate, it looks to me like we have alcohol groups or OH groups. And we also have this blue hydrogen that's still present. But this hydrate is forming in the presence of Jones reagent. So think about it this way. You've got 100 molecules of your primary alcohol to start the reaction. You dump in your Jones reagent and you press play. And it's not like this reaction is instantaneous, where all the molecules change at the exact same time. For most of the reaction, you're actually gradually decreasing the amount of starting material and converting it into product, which means that for most of the time of the reaction, your starting material, your initial product, and your reagents are all present inside your flask at the same time. And that means that in some cases, the products that you make can react again with the reactants. That's what we actually see in this case. Once we make a little bit of aldehyde, it gets converted into a hydrate, and the Jones reagent, specifically the chromium, can either react with one of these OH groups in the hydrate or one of your primary alcohols again. So if we look at what's going to happen if we took the hydrate and reacted it with our chromium, actually I'll write that out. Now we can see that if I remove this blue hydrogen and let's say the hydrogen on this oxygen, I'll make a new CO double bond, the other OH group will stay there, and that's going to end up being my carboxylic acid. So let's look at this from an oxidation level perspective. Our carbon that we're oxidizing here starts out at the C+1 level. In the aldehyde, that carbon is at the C+2 level. But in our carboxylic acid, that same carbon is at the C+3 level. Interesting. So what we can conclude here is that the Jones reagent, or the Jones oxidation, can oxidize primary alcohols twice. So we're going from +1 all the way to +3. Sometimes we call this like a double oxidation because we're changing two different levels. But we also saw that in the previous section of the video that with secondary alcohols, oxidation only happens once. Here's why these blue hydrogens are so important. The Jones oxidation will remove all of the blue hydrogens of your alcohol. So if you have two of them, you'll do two oxidations. If you only have one of them, you'll just do one oxidation. So Jones will remove all CHs on alcohols, in parentheses, blue hydrogens. And could oxidize more than once. Right, so just to reiterate, this is part of the reason why drawing these hydrogens that are a part of the alcohol group in is so important, is that it allows you to predict what the Jones oxidation is likely to do. So to summarize all of this, let's look at a practice problem. And in that structure, we'll put together most of what we've discussed so far with respect to the Jones oxidation. So let's look at a compound that looks a little bit more complex. So let's say we took this compound, so three different alcohol groups now, here, here, and here. And let's react this with the Jones oxidation reagents. And let's say that we're going to use a large excess of the Jones oxidation reagent. So maybe if we have 1 mole of this compound, we would have like 10 or 20 moles of the chromium trioxide and the sulfuric acid in the water. So that means that like basically every reaction that in principle could happen will. We're never going to run out of the Jones reagent until all the possible oxidations have happened. So I'll write that as excess. What I'd like for you to do is pause your video, and I want you to predict the structure of the product that you would isolate from this reaction, remembering that since you have so much Jones oxidation reagent present, you'd have to consider whether reactions could happen at more than one place in this molecule, and not only that, but how many reactions could happen at a particular site within the molecule. So what we need to do first is annotate the structure, and what I want to do is actually find out where those so-called blue hydrogens are, because that'll be a guide for me to know how to change the structure in the products. So working from right to left, in our primary alcohol, we have 2 of these. In our secondary alcohol, we have 1 of these blue hydrogens, and in our tertiary alcohol, we have no blue hydrogens. So that tells me that this carbon here, which I'm going to label 1 for primary alcohol, I'm going to oxidize twice. So that's C+1 to C+3, because I've got 2 blue hydrogens. And carbon 2, which is our secondary alcohol carbon, I'm going to oxidize once from C+1 to C+2 because I've only got 1 blue hydrogen. And in my third carbon, which is our tertiary center, I'm going to oxidize None, because I have no blue hydrogens. C plus 1 to C plus 1. So being able to actually look at these blue hydrogens simplifies my life a little bit. I can also think about oxidizing twice as being correlated with an oxidation level change, and that tells me that if I'm going from C plus 1 of an alcohol, C plus 3 will be an acid, right? C plus 1 will be an alcohol, C plus 2 could be like an aldehyde or a ketone, right? That can help me too. So that means that my structure for the product will have all of the same CC bonds. The tertiary alcohol will stay the same, right? This reaction can't work if there's no hydrogen to remove in order to form another bond to oxygen. And it turns out that it's very difficult for these kinds of reactants to remove a carbon-carbon bond, right? So we're really going to be focusing on the CHs. On carbon 2, I'm going to end up with a ketone functional group, right? I have a secondary alcohol that's being converted into a carbon plus 2 level. That's going to be a ketone. And then finally, at carbon number 1, I'm going to remove both of these blue hydrogens and get all the way up to a carboxylic acid functional group. So I have something that looks like this. And finally, just to check my work, I'm going to make sure that everything looks correct. I'm going to put my carbon numbering in. There should be no blue hydrogens anywhere in the structure now. Remember that the Jones reagent will remove as many as there are present on a carbon of an alcohol. So one thing I would encourage you to do, especially as we go forward in the semester, is not to just memorize every permutation of reaction. So that would be something like primary alcohol goes to carboxylic acid with the Jones reagent, and primary or secondary alcohol goes to a ketone with the Jones reagent, and tertiary alcohol doesn't react with the Jones reagent, because it turns out we're going to talk about other oxidizing reagents, and that means you're going to have like 9 permutations to memorize. The reason that I'm talking about oxidation levels and using the blue hydrogens is that I have to remember like 2 things now, and then I can implement it much more easily than working purely from memory. So it's not that I'm saying you should memorize nothing. Unfortunately, that's just not the way that synthetic chemistry works. Like there are these concepts of reactivity that are observations we've made. There's no way to derive them. You kind of just have to know them. I know that's frustrating. But let's try to make it a little bit easier on ourselves by developing organizing principles so that we can derive specific examples from those organizing principles. It's less to remember, and it turns out that it's a lot more flexible.